Hi, my name is Bohyun. I'm a PhD student working as a research assistant for Cyber Physical Power and Energy System Laboratory at Texas A&M University, Kingsville. The title of our team's work is Device-Centric Firmware Malware Detection for Smart Inverters using Deep Transfer Learning. This slide shows an outline for this presentation. After introducing current firmware security issues on smart inverters, potential firmware malware attacks and impacts will be discussed. A deep transfer learning method is proposed to detect malicious firmware malware at a device level proactively. So detailed information on this method and its validation will be covered. Then this presentation will be concluded by addressing future works. With increasing DER system integrations, future power grids will be more smart inverter dominant. Therefore, more remote firmware updates are anticipated for reliable system patching and managing located in geographically dispersed DER sites. However, advanced firmware malware attacks, such as moonbounce, targeting SPI flash memory, are recently disclosed after bypassing traditional OS-level detection methods. Also, our team has checked that obfuscated firmware malware could easily evade detections provided by well-known anti-malware services such as VirusTotal. In addition, firmware security research for smart inverters is less studied. 3 layers have been found from a hardware reverse engineering of a commercial smart inverter. Layer 1 is the network and application layer. And this layer includes SPI flash memory with a bootloader, an embedded Linux kernel, and file systems. Therefore, an OS malware attack or peripheral component firmware malware attack can be occurred by a malicious firmware update. Layer 2 is the conventional controller layer. Because of an MCU operated by RTOS in these layers, a controller firmware modification attack would occur, impacting layer 3, the power electronics hardware layer. Therefore, a firmware malware attack could preliminarily compromise SPI flash memory in L1 and then proliferate to MCU in L2 through the SCI interface. From a software reverse engineering of this smart inverter, a firmware update process was checked. A vendor sends a compressed or encrypted new firmware image over the air or physical access. Then, device bootloader in SPI flash memory decompresses, decrypts, verifies, and stores the received image. After that, the compressed subfiles from the image patches corresponding to target components. So in this work, these subfiles are target for the proposed deep transfer learning method. 3 vulnerable points were found from threat modeling on this smart inverter. This table's first vulnerability was used to dump a firmware image from the SPI flash memory directly. Again, the TTL method is proposed to detect malicious firmware malware at the device level proactively. The DTL utilizes a deep learning model designed by malware detection or classification as a basis model. In this work, VGG16 model was chosen as the basis model, which is pre-trained by publicly available malware files. Because the DTL method can accelerate training time with reducing parameters and architecture search for deep neural networks, it is appropriate for implementation on low computational IoT devices. Also, this method maintains high classification performance on a small data set, so it is also suitable for rare smart inverter firmware malware datasets. UART and JTAG debugging ports and direct flash memory chip techniques are commonly used to dump a firmware image stored in SPI flash memory. In this work, a firmware image was directly dumped from the SPI flash memory without a desoldering chip using FlashROM open source tool. This figure indicates all target subfiles are completely decompressed or decrypted, showing the entropy level is less than 1, but close to 0. The DTL freezes a portion of the deep learning layers, and the last few layers are retrained on the image datasets. In this process, hyperparameters of convolution blocks, including loss function, optimizer, and learning rates, are transferred to the DTL model. Then, fully connected FC layer in the CNN model layers is used to find an accurate classification result with fine-tuning when a new image dataset is provided. For the DTL test, 1 goodware and 4 malware variants are used for data samples. The left side figure is an experimental setup on an emulated smart inverter security test bed. The right side figure shows a penetration experiment result. After compromising the network and application layer by a backdoor malware, the controller layer and power electronics hardware layer are maliciously impacted by controller firmware modification. For the basis deep learning model experiment, a high computational local control server is used with 100 benign firmware files and 100 firmware malware. The ratio of training and validation is 50% separately. However, for the proposed deep transfer learning model experiment, an IoT device, Raspberry Pi 4B, was used with 1 benign firmware file and 4 firmware malware. The left side figure depicts the accuracy results of the training and validation of the DTL detection model for 40 epochs using the device-centric dataset. The training and validation accuracy values converged to 99% and 98% respectively. The CNN model trained by the DTL method was also implemented on the IoT device. As a result, all data set was precisely classified. These results show that the proposed method is accurate and suitable for device-centric malware file detection for smart inverters. In conclusion, the proposed DTL method enables to detect firmware malware with high accuracy and minimum time and effort at a device level. Future work include 1. Investigating more practical attack scenarios. 2. Studying malware variant and obfuscation techniques to generate potential firmware malware. 3. Lightweight and high accuracy detection algorithm development to be implemented on smart inverters. And 4. Developing forensic and recovery techniques for the smart inverters. And this research work has been funded by the US Department of Energy Solar Energy Technologies Office. That's all I have for this presentation, and thank you very much.